everybody. Welcome to this week's CEDAR seminar. We are delighted to host Alex Shkolnik from UC Santa Barbara, talking on a very familiar and important topic. Whose title is right up there on the screen, and I won't take any more of your time. Thanks for coming, and please go ahead.
So thanks so much for the invitation. This is a homecoming for me. Last time I gave a talk here was when I was a postdoc, I believe.
What about in the math department? You don't want to count that?
I mean, like here
in this seminar.
on this floor. So this is a project that that has in many ways been initiated when I was here as a postdoc, working with Lisa and Alex in the back. The topic is the Markowitz optimization enigma. It's joint work with Gorgodon. And so I really want to give a lot of credit to him. Without him, this project definitely wouldn't have happened, and it wouldn't be possible to get the results that we have. On top of the kind of the paper that we're writing on the first page, we have. Oh, I'm not able to switch slides. Oh, sorry. Not off there.
Yes, we're not masters of
Sorry, guys.
Was it because of the sharing?
Why is it?
What if you push buttons on the laptop? Can you switch sides from the laptop? Yeah. Want to just do it that way, Alex? Is that too hard?
Oh, no,
Oh, it works.
Oh, it
Okay. All right.
Thank you.
So everything I said, and we're gonna resume. So the paper that we're writing now, which has the theory parts in and maybe not the numerical results, which are currently in progress. I'll show some of those today. We're on top of the paper trying to dedicate it to Harry Markowitz. And same goes for the talk. So I want to first describe what I mean when I say the Markowitz optimization enigma. And as we all know, Markowitz's kind of main contribution was to pose portfolio construction as a problem as a trade-off between giving the return and between the risk. So we see the efficient frontier there, and the Markowitz enigma refers to the estimation of this frontier and how difficult it is in the presence of estimation error. So I wrote there that given a covariance matrix, the computation of the efficient frontier is a simple solution of a quadratic program. But what makes this process difficult is when that covariance matrix, the one I'm highlighting right here, has estimation error. The phrase Markowitz enigma, at least as I understand, comes from a paper by Richard Michaud in 1989, where he says that this phenomenon entails the observation that risk variance maximizers, risk variance minimizers are fundamentally estimation error maximizers. And that's the title of the paper, and you can read sort of his perspective on it. But back when I was a postdoc and working with Lisa and Alex, we've sort of phrased or gave a mathematical characterization of this phenomenon. And that's what I'm going to do today in a slightly more general setting. And to get started, we're going to look at this minimum variance program. So this is the point on the efficient frontier that achieves the minimum variance. We're minimizing sigma, the portfolio variance, subject to a fully invested constraint. And I guess I should set up some notation since it will be used throughout. The vector E is going to be the vector of all ones. I'm going to use this dot product notation and the length of a vector quite a bit. So hopefully that's all clear. And in that case, I can move on. the model that I'll be considering is this one. So since security returns decompose into a systematic and specific component, we can assume the same goes for the covariance matrix. So here we're looking at two parts, BB transpose and the omega. This talk is mostly going to be focused on this first leading component. This is a P by Q matrix. P is going to denote the number of securities, number of assets. Q is going to denote the number of risk factors. And by risk factors, I literally mean high dimensional vectors that stack the columns of that matrix. They're called market risk, different style factor risk, industry risk, climate tech innovations, and so on. So ChatGPT is perhaps a risk factor for various parts of the financial sector. So why is this decomposition the way it is, and what is how do these two components that I'm looking at, how are they different? It really comes down to eigenvalues. So when we think about matrices, we're thinking about eigenvalues and how quickly eigenvalues grow. This omega matrix, its only characteristic, as far as I'm concerned, is going to be the fact that its eigenvalues are bounded in the dimension. So as the size of that matrix grows, the eigenvalues or the spectral radius is going to be bounded. And that assumption is sort of in finance speak is equivalent to the fact that specific risk may be diversified away naively. Naively meaning by like an equally weighted portfolio. The systematic risk may not be, and that's the difference between the leading component, the BB transpose. The eigenvalues of BB transpose are going to diverge. And I'm borrowing this from a very influential paper by Chamberlain and Rothschild, which places these exact assumptions. So this is sort of the mathematical version of what I just said. The first part is saying that specific risk can be diversified away naively. The second part is saying that the eigenvalues of BB transpose grow. And the reason it says that is because I took the dual of this matrix, B transpose B, divide by B, and assume that this limit exists and is invertible. This condition is equivalent to the eigenvalues growing linearly with the dimension. And that's an assumption that's going to be in place throughout. This is called an approximate factor model in the literature. I won't discuss it too much, but it has all sorts of connections to arbitrage pricing theory and so on. But I want to move on to what I'm concerned about here, which is the estimation of the covariance matrix sigma. And so we saw that while sigma splits into two parts, BB transpose plus omega, it makes sense to do the same decomposition for the estimate. And the estimated components, I'm going to be calling H and just a little number omega. So I'll make a couple of comments here, which is that since I'm focused on the estimation of risk factors, I'm primarily going to be thinking about this matrix H, which is estimating the matrix E. Here I say that the simple estimate and number omega squared times I, the identity of big omega, is going to suffice. And I'll explain during the talk why that's true. But this is essentially what we're going to be doing. We're not concerned about estimating that complicated matrix omega with bounded eigenvalues. And we're just going to say it's going to be good enough, and we'll see why, for our purposes, to just put a scalar matrix there. And the assumption H here that you see is just kind of mimicking what the previous approximate factor model assumption was on B. So we're basically saying if H is an estimate of B, it should satisfy an assumption that's sort of similar. Some of this notation is, a little bit out of order. Let's not, I guess, worry about what EH means. I'll cover it eventually. I think the limit of that matrix existing and being invertible is the kind of the part that I'm highlighting. So the first variable that we're going to be thinking about with respect to the Markowitz Enigma is the true risk of the portfolio. And so by true, the reason the word true is here is because the sigma that's in that quadratic form there, it's the unknown. That's the true covariance matrix, which we don't actually have access to in practice. And the hat on the portfolio is indicating that that portfolio was constructed with sigma hat, and therefore W hat carries estimation error. And so at this point, you can pause and try to ask, what is the behavior of the true risk, that quantity V, subscript P? What is its behavior as the portfolio grows, or as the dimension grows, as P becomes very, very large? You can ask that question. You can also ask which entries of the estimated covariance matrix the sigma hat, are most responsible for whatever behavior is going to manifest itself. And finally, you could make a direct comparison to something that we do know in practice, which is estimated risk. So the quantity on the bottom, the sigma hat P, that thing we know in practice. We can actually take the estimated portfolio W hat, compute that quadratic form, because in the middle sits an estimated covariance matrix sigma hat. So that is what we think the risk is. And up on top, the VP, that's the unknown, but it's also the true risk. And those are the two quantities that in this mathematical characterization of the Markowitz Enigma I want to focus on, and hopefully, yeah. So if this is the right slide, I'll do a little bit of notation. So this asymptotic notation on top is basically saying that the two quantities on the left and right-hand side, so for those who are on Zoom, I guess you cannot maybe see me highlighting this, but I'm highlighting the left-hand side of the formula, the ratio of the true risk over the estimated risk. The left and the right-hand side are on the same order. So there's like a constant separating them as P goes to infinity. And now if we look at the right-hand side, we see that this ratio of the true risk over what we think the risk is 1 plus some function that I'm going to define later times P, the dimension. And so it's saying that the conception of risk that is actually there relative to the one that you think is there is diverging. Those two values are growing further and further apart as you take more and more stocks or more securities into your portfolio. So this is our kind of characterization of the Markowitz Enigma that we started with Lisa and Alex in the audience, and that we observed on a very simple problem where H was just a single vector. But today I'm going to be discussing the case of H having many risk factors, any number Q of columns. The other difference from that original work is that this function E, the curly E, cursive E, which we are going to call the optimization bias, is now a vector quantity. And it's a vector because it's an optimization bias or an optimization error with respect to each risk factor. So it's going to be a vector of Q components, one for each individual risk factor. And when we think about the ratio of true risk over estimated risk, we're going to compute the length of that vector. That's what that notation means, the two absolute values. That's the length of the vector squared times P, right? And that multiplier P is going to really grow that difference, provided that this optimization bias, this curly E, is bounded away from zero. When I talk about roots, I'm talking about literally the zeros of that vector function. We need that value to go to zero in order to bound this ratio. That should be obvious. The length of this optimization bias vector has to go to zero in order for us to keep this ratio on the left-hand side bounded. Yeah, and like I say at the end there, that this ratio is going to diverge unless we do find a sufficiently good estimate. It's going to turn out that finding roots of this optimization bias function is going to be very difficult and counterintuitive. And I'll explain how to do that in one dimension when Q equals 1, and I'll try to do my best to explain it to you, what happens when you go to Q equals 2, 3, 4, and so on. So that's sort of the aim of the talk, the goal of the talk. I haven't actually mentioned anything about estimation methods. Those are going to be PCA, but right now the talk is sort of method free. So you could think about any method of estimating H. This would happen unless that method produces an H in such a way as to set the optimization bias, the function E, to 0. Yes.
You have a vector, this EP, and does it depend on those risk factors being uncorrelated?
Being
uncorrelated.
I'm going to address all that. We're going to take a deep dive into that function, and I'll go through exactly what it depends on, and I think it'll answer your question.
Yeah. Question. So are you assuming that we know the true value of Q, the number of factors, even now?
So I'm actually going to have listed as an assumption. We have not done anything about misspecifying the number of factors. We haven't even tried it in simulation. We're still kind of putting together the first set of simulation results. I have no idea what happens when there are 8 real factors, but you say it's actually 7. No idea. But we do kind of say that that's an important problem that we're just not going to address. So yeah, great question. Thanks, guys.
Just a clarification question.
Yeah.
You think that the true risk is equal to the estimated risk if the E function tends to 0?
Yeah, so I think that's right. The one caveat here is that notation that I wrote down, it's kind of keeping a constant hidden. So it's sort of like they're on the same order. Like when I say 1, I really mean the constant. And remember when I said the estimate of specific risk doesn't matter? That's where it matters. So it's like a second order thing. Once you handle this function E, then you can start worrying about that leading constant and the specific risk estimate. Yeah.
Thank you.
Yep.
What's the dimension of E?
E is a Q vector, so it has Q components, one for each risk factor.
Thanks.
I didn't know a Zoom could ask questions. This is a really good Zoom setup. I mean, aside from the stumbles in the beginning, but that was my fault. All right. So before we get into methods and solutions, I want to outline this hierarchy of challenges. We kind of write about this in the introduction of the paper. The hierarchy of challenges is like, we're going to try to produce an estimate H. So the hierarchy is kind of saying like, how good does this thing have to be? And we have a whole prize system here. So if you want to kind of, take your favorite method and undertake this challenge, you kind of can see what prize to aim for. The grand prize is awarded to H sharp, for which P times that vanishes. So this is P times, you can think about the length of that vector E, or you can think about, just Q entries multiplied by P. But if that vanishes, or maybe it's even 0 for some finite P, that's the best you can do. I mean, that would be very impressive in my opinion. In fact, I would say that, well, actually, I shouldn't say that, but I'm gonna move on. I shouldn't talk too much. I'm gonna get in trouble. So it's clear with the.
Just to the clarification, was
Yes.
Q fixed as P grew?
Yes, Q is fixed. Yeah. At least I don't know how much it would matter. If it grows, I'm gonna make the assumption it's probably not gonna matter too much if it grows very slowly relative to P, but I wouldn't let it grow with Q.
Right, but the point is, it's the P that's really the.
P is growing, Q is fixed. Yeah.
Yeah, that's a
But
pretty reasonable
it's-
assumption.
yeah.
If you have like the S&P 500 or the Russell 3000 or the Wilshire 5000,
I
you
mean,
wouldn't think
yeah.
there are that many different risk factors.
Especially if you're looking at orthogonal risk factors, that kind of the agreement in the literature that I'm aware of is the number of orthogonal risk factors in US equity markets is between 2 and 6.
Actually, I'm gonna take it back. As it grows, small caps, you're getting more and more small caps,
Yeah.
and they could actually behave
Yeah.
differently.
Yeah.
So we could consider looking at a.
Yeah. Yeah, all sorts of extensions.
Yeah, we could
Let's,
consider looking at a growing set of risk factors.
I think to just answer to be safe, I'm gonna take Q completely fixed as a number and it's never gonna move. Let's do
Yeah.
that, yeah.
So as P grows wider, there necessarily higher proportion of small cap stocks. I mean, you could grow anyway, you could.
Well, when I think of the way the 3 indexes I just said grow, the S&P 500 and
Granted that, but
I think that markets tend to be very concentrated. And I don't think you get a lot of new mega caps when you grow your size of your market. I mean, it seems not.
I mean, mathematically, one could imagine a model in which P is growing and half of the market cap is in the top.
It could be any which way, but we
Yeah.
haven't seen that.
Yeah. Okay,
That
that's fair.
it certainly could be in any which way, but it's not what we'll see.
So the subscript on H suggests that H is somehow parametrized by estimation methods. Is that right?
No, I just like the way it looked.
It's like a musical thing.
Yeah,
Yes, no, I'm familiar with sharps and flats, but when you say the grand prize is awarded to.
not a
the,
musical person, I just like the way it looked.
I
can play the
well,
guitar.
thanks for clearing that up, but
I wanted to
the
distinguish it
H.
from H, Nick, so this is just to distinguish it from H. H is like what your estimation method gives you. And then the point of the sharp is saying, like, let's say we put some bells and whistles on top.
Right.
Statistics, you have a lot of,
Whistle.
method whistles, a lot of whistles and a lot of bells. They're, robust covariance estimation and so on.
But then we're looking at a family of estimators and we're trying to find an estimator that has this wonderful property.
Sure.
Okay,
That's why we gave it a beautiful notation.
Well, yeah, I mean, I don't know if I'm kind of neglecting something, or do you want to rephrase if am I missing something, or what exactly, what's our kind of, let's tie the knot on this comment here. H sharp is like something that's based on H and maybe some other observable data. Is that fair? To make that estimate, original estimate H more robust in some way?
yeah, no, that's fine. So maybe the idea is we want to find an estimator of the form you just described, which will have this wonderful property. Okay.
Yeah, I didn't
thanks.
describe any form though, so like, I just have H, somebody gives me H, and then I have some bells and whistles that turn the H sharp, and the H sharp magically has this property that gets the first prize.
Great, thanks.
Second prize, and it's really here at this level of hierarchy where the estimate of omega matters. This kind of explains a little bit why I made that very simple estimate in the beginning, because once you go to second place and third place, it's not going to matter too much. Second place is just the thing that would bound this. So you want the ratio to be bounded. You just don't want the conception of true risk to estimated risk to diverge. That second place and third place would be, let's just get it to 0 and be happy with that. And then maybe this ratio diverges, maybe not. It depends at the rate at which goes to 0. So you're kind of, taking a less ambitious goal and saying, let's get this to go to 0. And then we'll worry about the rate at which it goes to 0 and hope that, maybe in practice it goes to 0 sufficiently fast. When I say this may seem insufficient, I mean in terms of that risk ratio. And when I say it has merit is in a way that I think I'm going to explain in a later slide, hopefully soon. I don't quite remember. Let's see. Yeah, I think it's here that I'm explaining it.
That's right.
What is the, perfect. Okay, I was shifting things around. I'm very tired. So what's the merit of third place? So one thing is like, maybe you get that property and in practice, it's way better. So like you think you place third, but you actually place second, but there's more. And to describe what I mean by more, we're going to look at the eigenvalue decomposition, or just the eigen decomposition of the systematic component, the BB transpose. So like these risk factors, when they come in, somebody just gave me a bunch of columns. It goes back to Lisa's question about things being orthogonal. I'm not assuming that. Like you literally put anything in those columns, make sure the eigenvalues grow, and I'm happy. But in order to write the mathematics, we're going to have to put things in a structure. So we're going to have to think about directions in space that are orthogonal, and also orthonormal in the sense that they're directions, meaning like unit length vectors, and also the variances. So these are eigenvalues and eigenvectors, and that's all I'm writing. So the cursive B is just the columns that represent the eigenvectors of BB transpose. The lambda are the eigenvalues, which by assumption M, right, that Chamberlain-Rothschild assumption, are going to now grow linearly with P. So it's just a different way to rewrite things, and it's going to help me because in this lemma, under assumptions M and H, we have two things. The estimated risk decays. There's a subscript P missing on the sigma hat. Apologies. But that thing is decaying at the rate of 1 over square root of P. So the estimated risk, what you think the risk is going to 0. The true risk depends on this length. So let me break it down. The first part is lambda P, the square root of P. So the square, you notice the square on the lambda is missing. This quantity, this ratio, lambda P over square root of P, is bounded because lambda grows proportionally to the square root of P. And multiplying it is again this mysterious optimization bias vector, which I'm going to get to eventually. And when you take its length, this value is going to describe the risk of your portfolio, or the volatility in this case, right? V without the square is the volatility of the portfolio, the true volatility. So what do I mean by merit? The third place gets a riskless portfolio in the infinite dimensional limit. So as P goes all the way to infinity, if we manage to get third place, the risk of the portfolio goes to 0, which is then consistent with what the estimation risk is also telling me. And that's what I mean by merit. Maybe you didn't get the ratio right, but at least you have this result where you have a riskless portfolio for once you have many securities.
So the ratio might go to infinity, but it's basically. Yeah,
But
it's riskless, so you.
Yeah.
You think it's really riskless and it's only.
Yeah, that's the bad point. That's not the merit point. Yeah, that's right. Yeah. So it's merit, but yeah, there are caveats, right? So, but it's something, right? It's better than having positive risk.
So, I'm trying to now understand assumption examination in this context. So I could imagine a model in which I just clone the stock. So, in my nth economy, I start off with Q stocks.
Wait, P stocks.
P stop.
No, I start off with Q's number of factors.
Q number.
I start off with Q stocks,
Mhm.
and then my nth economy, I have n times Q stocks, and they're all clones of the ones in the original.
Yeah.
Thing.
I don't like the word clone because this is not going to give me a full rank matrix B. Is that where you're going or maybe not?
I think that's giving you a full Q by Q rank matrix.
Okay, then we're okay. Yeah. And then next question we do is eigenvalues grow with B, or I saw the criteria for B and that assumption is the following. You give me a matrix B and I check two things. The length squared of each column grow with P. That's check mark 1. Check mark 2, full rank.
So we,
So the puzzle for me is that I think in my clone example, there isn't a riskless portfolio.
So that's interesting. I will not be able to obviously figure it out.
Maybe that's not right, because you assume the Q by Q matrix is full rank, and that maybe guarantees the riskless portfolio, assuming there's no estimation error. So I take it back.
Okay, I'm confident in the lemma. If you have a counterexample, I'm happy to hear it, but I'm confident in the result. But also obviously we could have made a mistake. Anyway, so that concludes kind of this is sort of the introduction of what we're going to do. I think this is what we're going to do today. Eventually, I'm going to place third. We're going to place third together, and we're going to do this. Oh, I didn't mention here. We're going to do this for PCA, principal component analysis. I should have said that. It says here that in a simulation, in a kind of a toy model simulation, meaning that we have Gaussian returns, which is not all that realistic, we're actually going to exhibit all the properties of the second place, maybe even first. You'll see. You will be the judge of what happens in simulation. I'll show you some preliminary numbers from this weekend, actually. But the proof that the theory is all going to be about third place in principal component analysis. Oh, okay, yeah. I was hoping for a catchy title. Bad matrix. So bad matrix is a reminder to me to discuss when you have an estimated matrix sigma hat. I earlier asked the question, which entries of it are like responsible? And now we know what it means, what we're going to be responsible for. It's this Markowitz Enigma effect, where the ratio of the risk diverges. So we're now asking the question, what is it in sigma hat that's going to be responsible for this behavior? And that's what I mean by bad matrix. So again, this is the proposition about what's happening when P grows. And we're going to look side by side at the true covariance sigma and the estimated covariance sigma hat. And we're trying to understand what is in the structure of these two that's making the difference. And the first clue, the fact that I replaced the big omega with a little omega, just a number, that's the first clue that that's not where the problem sits. And in fact, you can be completely off on your little omega estimate, or you can put any estimate omega hat in there as long as it has bounded eigenvalues. So you put something in there that's even like remotely reasonable, that is not going to be the thing that's going to get you the Markowitz Enigma. That's not what's responsible for that proposition. What's responsible for that proposition are the entries of H. And we're going to try to say like which ones or what parts of it. And the first thing that we're going to do, I need to go through a little bit of, I need to go through a little bit of math to kind of also set up things that are upcoming. And this is also getting a first glimpse at what the optimization bias, what this vector looks like. So let's spend a little bit of time here. just to review again, we have the systematic component BB transpose, and I'm writing its eigenvalue decomposition with the curly B and the lambda being the eigenvalues. And now I have the right-hand side of the optimization bias under the scale square root of P, and it looks just like this. The E is the vector of all ones, hopefully you remember that. EH is something I'm going to explain. For now, EH denotes the projection of E onto the span, the column span of H. So like, how do we think about this? You think about a vector is like, a line in space, and I want to project a point onto it. I just, do the best orthogonal thing I can, make the 90-degree and shrink to that line. That's the projection. You want to project a plane, and you go to the shortest distance possible to that plane, and so on. That's what this operator is going to be doing. And it's going to be very handy for us to do a lot of the mathematics that's underneath. So this is the formulas and that's involved. Once we figured out this notation, and Nick, maybe you're going to like the dagger notation. We have sharps and daggers, so there's more it looks nice in my opinion. But once we figured this notation out, a lot of the math just started working out kind of itself. So each EH is H times H dagger, where H dagger is the Monroe-Penrose inverse. And that's a projection operator. That's exactly.
Just a linear regression.
Sure, yes, yeah. Depends on who we talk.
For those you're talking.
We're not on the,
Hidden in the audience
if we
or
go
something.
down to fourth floor, then.
It's a
we don't-
different, yeah, but
I don't know what it is in economics, but yeah,
looks like
but-
a regression.
yeah, sure. Projection, least squares, whatever you want to call it, right? So we're taking a vector and we're getting the closest element of it in the span of the columns of H. We can do that not just to vectors, we can do that to a matrix B.
Yeah.
And here's the thing that's going to make everything work, and without which we'd be completely lost, is this lemma. This projection operator is invariant under invertible transformations. So if you have an invertible matrix K, the projection of E onto H is the same as the projection of E onto H times K. So for now, this may seem like kind of remote and insignificant. This is going to play a role many, many times over when we actually try to work the math. And that's why I'm introducing it now. You're going to see it appear at the end of the talk. Hopefully it makes sense. The way to prove it is very easy. You just plug things in and start calculating until it works and rely on the fact that K has an inverse.
Is
So that
that
was a
just,
little-
is that just a statement about change of basis that? It's a
Yeah, it should be.
projection?
Yes.
Okay.
Exactly. Okay, so let me back up a little bit. So this is the EH that's appearing in this optimization bias formula. You work it out. All of this is worked out through just direct calculations and taking limits. Not going to show the math here, but this is just the things that pop out once you start computing those asymptotics. And here's what we're going to do. We're going to get even more insight into the optimization bias by choosing a very specific K. So first thing I'm going to do is I'm going to look at the systematic risk component on the estimation side. That's the HH transpose. The curly H, consistently with the curly B, is going to denote the eigenvectors of that estimated systematic risk matrix. The S are going to be the eigenvalues. So just notation is curly H is P by Q. The columns of it are orthonormal, so the columns have length 1 and they're orthogonal. And they're essentially the principal components of that matrix. That's one way you could think about it. They're the eigenvectors, and the eigenvalues are S, and they're all put into this matrix S squared. So S squared is a diagonal matrix of eigenvalues. Those also grow with P. And now if we apply that lemma with K equals S inverse, you'll get another form of the optimization bias. Don't worry if you're not following it, it's just kind of rewriting things in different notation. The question is why we're doing this. Remember I said bad matrix. We're trying to figure out what's responsible. So what we've just isolated are two parts of H, the directions and the lengths, right? The variances and the lengths. And what we just saw is that the optimization bias doesn't depend on the variances or the lengths. It only depends on the directions. So we just got down to the root of the problem. That ratio, I don't know if I have this on the next slide or not. Oh, there we go. That's nice. Yeah, perfect. So this optimization bias, which is going to determine the ratio of true to estimated risk, has the following properties. It does not depend on the specific risk estimate. You can get that as wrong as you want. I mean, maybe not ridiculously wrong, but reasonably wrong. As long as it washes away when you take p to infinity, it's fine, right? So as long as those errors wash away. It does not depend on the lengths of the columns of H. Like the size of H doesn't matter. It's only the directions, once orthogonalized, that determine. So the span, right? The span of the column span of H. That's the only thing that's going to matter. And that's what I wrote at the end. Bad matrix means, bad directions of the columns. So we've just isolated the root of the problem. We've said the size doesn't matter. It's just the directions of the systematic risk. Another question. Did you have a question? Or?
No, well, maybe it's just really the bad span, the span of the bad directions or the directions.
The span is bad, yeah.
The span of them, like the directions could be all wrong, but if their span were right.
Yeah, true too. Yeah, but I
So-
don't, yeah, that's a better way to phrase it. You're right. It's
Okay.
not, yeah, when I say directions, I mean like orthogonal directions, because I'm already thinking PCA, but you're right.
But yeah,
The
so
span,
you got some columns, you take their
Fair.
span, it's either a bad
Fair,
span
fair.
or a good span.
Very fair, yeah, very common. I agree,
Okay.
yeah, I agree. That's a better way to say it. Bad span. Game over for PCA. I'm gonna do a very quick thing on PCA and why that doesn't work very well. So what's PCA? I don't want to spend too much time on this. I'll just run through this kind of quickly. So one way you can look at it as a reconstruction error. You take your data, this is on top. I'm looking at the difference in Frobenius storm of the data minus the data projected onto the column span of H. So I'm projecting the data onto a low dimensional space. I'm taking the difference and I'm looking at the norm of that. That's essentially almost PCA. The reason I'm writing this is that if you look at H is equal to B, provided that the error is 0. Oh, and I didn't cover what the model was. Whoops. I'm going to back up a little bit. The Y that you see on top, that is a security returns matrix. It's P by N. N is now a new variable. It's the number of observations. So you have a data matrix Y, P rows, those are the security returns, and the columns are the dates, returns on day 1, day 2, all the way through N. Sorry, I admitted that. And the reason that the right-hand side of that Y equation is grayed out is because that's the stuff that I don't observe. That's like an assumption, a modeling assumption, but I don't get to see the X, I don't get to see the E, I don't get to see the B, anything like that. The E is the error or the specific return. And what's written there is that if the specific where the error return is 0, then that mathematical program returns non-uniquely, but it returns a solution, or one solution of it is B. And that motivates PCA. It's kind of saying if the error is small, you'll do good by solving this. And PCA adds only one additional ingredient, which is let's make the directions orthogonal. So let's make the H estimate the orthogonal, and this is going to correspond to the eigenvalue decomposition of a sample covariance matrix. So I've said kind of a lot. I wish I kind of said it faster. In the end, I'm taking a data matrix Y, I'm making a sample covariance matrix S, and I'm going to take the first Q principal components, the first Q eigenvectors and eigenvalues of that matrix. And I'm going to take, so how would you make H from this? Well, you can take the eigenvectors, multiply by square root of eigenvalue, and you get your H. Right? Curly H, remember, is unit length. The non-curly H has a size associated with it. So hopefully that's clear enough. Kind of stumbled through that a little bit. But on the next slide, I have sort of a recapitulation of what I just said. The eigenvalues are the S's, so S squares, 1 through P, those are kind of the ordered eigenvalues. And the S matrix are the first Q of them. So S squared is a diagonal matrix with the first Q largest eigenvalues. And now here's the relationship between the H and the curly H. You take the curly H, you multiply it by square root of the eigenvalues, you get H. And you can go back and forth between those two. So I'm getting rid of the growth, the size, the thing that grows with P, and just isolating the directions when I go to the curly H. This quantity at the kappa squared, that's like a residual variance. Like, what am I doing there? I'm taking all of the eigenvalues after the Q factors and averaging them. So that's like the residual risk, sort of. So remember that number kappa, it's not terribly important. I'm going to use it. But for now, we can say that it is going to be a very simple-minded way, but a good way, of making a specific risk estimate. So you see there at the end, this is all I want to get to. This is a PCA model. at least in PCA model. I took my eigenvectors and eigenvalues and put them in the systematic component. And I took the residual risk and made a specific risk out of that because I don't care how good that's going to be, even though that one is actually a pretty decent. I say there that it estimates the trace of the omega. That's true under some assumptions, which I'll share, but I don't want to get hung up on that point. This is going to be the simulation study. I'm going to simulate a bunch of returns that simulate that matrix Y. I'm going to assemble that PCA model, just how I've described. I'm going to compute the minimum variance portfolio by looking at only at the data, looking only at the PCA model, the sigma hat. And then since we are in the simulation context, we actually have the true sigma, so we can run this experiment. And unfortunately, in the current kind of version of the numerics, we took a square root, which is probably not the best. The Markowitz Enigma had a square, both the top and the numerator were squared. So when you see these numbers, it's helpful to square them. They're going to be bigger, which is more. I wish I did that, but I didn't have enough time. But yeah, so we're going to look at the first table now. Huh? Oh no, we're not. We're going to look at how I made the model. Okay, so this is an 8-factor model. It has a market. I can give you the specifics of what goes in here, but I'd rather go over it quickly. You can just ask me for specifics of what's in the actual code. But the first column is a market risk. This means that in the first column of B, we're going to put like entries that are roughly 1. Actually, roughly 1 times like 16, which is the volatility in US equities. But you're thinking of what my 16% annually.
Oh.
Yeah.
Okay.
I didn't want to get into numbers. I kind of wanted to just go through this. So the structure of that vector is a lot of positive entries, let's say that way. The next 3 are called style factors. Those are going to be kind of dispersed around 0. So some, a lot negative, a lot of positive entries. That's the next 3 columns. And the last ones are industry membership. So what we do there is we go to each stock, we flip a coin, and we put a 0 or 1. Are you in this industry? Right. So we have, 4 industries, 4 columns. And we're going to flip a coin for each one. Are you in or are you out? Are you in the
It
auto?
can be in only one industry, right? You let the stock be in a bunch of industries.
Yeah, they can overlap. Yeah, you can.
But then you have to make it add up to 1, have it be like a bar model.
We didn't. This is very kind of rushed. So
It's a
I'm going to
bar-ish model.
bar-ish model. Yeah. So yeah,
We could talk about this.
I want to get this right, but yeah. So
And did you simulate idiosyncratic returns or not?
I did absolutely. I mean, it's not mentioned here. I got rid of it from the slide. The point is to say that when I say Gaussian returns, we took the factor returns to be Gaussian, and we took the specific return to be Gaussian. I can kind of speculate on what will happen with a heavier tail distribution, but I'd rather not for now.
And you think of these as log returns, so.
Oh, no.
Totally not. That would be a disaster. It's a disaster because the weighted sum of log returns isn't the portfolio log return.
No,
I know you know that.
Yeah.
But it would be catastrophic.
So basically, you're assuming stock returns are Gaussian, not log normal.
Yes.
Correct.
Okay.
Returns
It's
are
the
normal.
industry standard.
All right.
But we don't, I can give you a little bit of insight into what would happen if you use a student T distribution, but for now, this is like, we're getting early kind of
I'm not interested in T.
Sure.
I'm doing
log normal, yeah.
log normal versus Gaussian.
But
Yeah. all
yeah,
right.
I don't have.
Okay.
There are problems with using this Gaussian distribution.
Yeah.
Well, there's problems with, like, this is.
So think of this as a very stylized simulation still. I think the big advancement here is that we're making the number of factors much larger than the previous work, which I'm going to talk about. And so this is like the big step forward is to add more risk factors.
Actually, you segued to simulation, but did you actually state the theorem? So
No, I know.
implicit theorems seem to be, there's a correction that.
There will be theorems, yeah, there will. But I'm doing PCA. I'm not doing any kind of. I'm doing stuff that's known. I haven't done anything about what we're doing yet. So right now it's just PCA, and everybody knows
It's gonna be
PCA.
at 4 o'clock.
Okay.
Did you guys keep interrupting it? Maybe.
Yeah.
All right. 8-factor model, Gaussian returns. We're going to look at a table, huh? Estimated risk. So we're looking at this. This should be easy. So we have P. That N is going to be. I didn't write it down. N is here is 60. So 60 returns, 60 days. Daily returns, 60 days. P is the size of the portfolio. We're moving from 500 to big number,
This is
16,000.
minimum variance, the minimum variance.
This is
we're
minimum
looking at.
variance, yeah, and we're looking at what we think the risk of that minimum variance is versus the true risk. And you can see that the estimated risk goes down as theory predicts. Or at least predicts for an estimator that is a
Yeah.
bad matrix.
Bad.
We haven't proved anything. I will have, like, one of the theorems will actually prove what happens with PCA under some assumptions, but for now, we're just looking at numerical evidence. Estimated risk goes down, true risk is kind of leveling off. There is a part of this study that I don't like, which is we're not, so we need to rewrite the code in the sense that this is not very consistent. When we move across rows, we're kind of starting over, which is not the right way to do this. When you see some of the numbers jump, this is because we just haven't had time to rewrite the code to grow the kind of everything in a consistent way. So what we really should be doing is we should be going down to the last row and then taking subsets of it and then going back up. And that's why you see some of the fluctuations, which is why we're still kind of stuck on the
If
numerical
you're
study.
taking expectations, it's not that bad.
Yes,
And when you
expectations,
do
yes.
More complicated problems doing, like I'm working on the thing you just said.
Yeah.
And it's in a slightly more complicated context. It's a huge pain in the neck.
So yeah, I couldn't update the tables over the weekend. I was busy
No,
and stuff, but yeah.
If you, when you do a more complicated optimization.
Yeah, of
problem
course, of
and
course,
you
of
keep
course.
it- That it gets into terrible trouble.
We can do it here, so we're gonna,
can do it
we
here.
can do it here and we're planning to, but yeah, but hopefully the message is clear. You can see the ratio blowing up, and if you square that, right, that's the Markowitz Enigma, those are big numbers. Right, I don't know what 13 squared is. Okay,
The true risk
13
is,
squared, you do know.
I'm tired.
the true risk is decreasing, but
Right.
very slowly.
This is should be square root of p. If the theory is right, this should be square root of p. Right, so according to the lemma that I wrote, you know, I'm not gonna try to verify this in my head right now, but it's, you know, we should, well, I'm doubling the number of stalks, the k should be square root of p. Right,
Well, I'm looking at 12.45 versus 12.32.
with 12, oh, no, that one is the true ratio.
Ratios look like
Oh, I
square, but these
Right,
don't, these look to
right,
be decreasing.
But that's confirming the lemma that I showed you. Remember you were saying you had a counter example? This is confirming on PCA that lemma. The fact that the true risk is gonna be asymptotically something bounded away from zero, right?
With the correction, it's,
Look, I'm not doing
All
correction yet, not yet. At 4 p.m. You gotta wait for 4.
yeah.
Yeah. Actually, no, you know what? I think I knew that this might happen and I wanted to show you the result right away. So I'm gonna show you the result now and then I'm gonna just keep talking and you will find out how to prove everything. And if you have to leave, I won't be offended. I know Shoulder's gonna go 12, but I'm gonna show you this is, what time is it? Already 12 or?
Well, yeah, but I'll stay.
Give me 2 minutes. I'm gonna show you the mystery, sneak peek at the mystery estimator sigma sharp. Here's the table. This is what we're able to do. So same data set, same process, just a different estimator that has a sharp. And you can see that the true risk and the estimated risk go down together in a very balanced way. The ratio remains fairly stable. Even at 500, you're kind of close to 1. This is actually suggesting second place, but we can't prove that. It's going to be difficult, but you know, next time. So that's the numerical evidence. And then one last thing is what does it look like? Complicated, but not bad. This formula has evolved over the past year. This is like as of like last month. I think this is the final product. This is about as aesthetic as it's going to get. Very beautiful, in my opinion. So you have this sigma squared, which is a function of a bunch of eigenvalues, this diagonal matrix, very simple. You start off with that. Then you have your eigenvectors and you put this theta matrix together. Pretty simple operation, just a matrix vector multiplies. This A plus or minus is just kind of a constant. And then this is like a formula for H sharp. Look at what it's doing. It's combining H, the PCA, the principal components, with this, this would be a rank 1 update, right? It's a rank 1 update to the principal components with this weird A plus A minus. It's a little complex, but here's what you get. You get the columns are orthonormal. So you can see at the end there I wrote H sharp transpose times H as identity. So these are truly corrected principal components. They're completely unit length and they're completely orthogonal. And it's a nice formula. You don't have to like write any optimization code or compute any kind of fancy things. It's just a plug-in kind of thing that you can code up very quickly. So that's I think that's it. Oh, there's a theorem. And I'll explain, the rest of the talk is like explaining this theorem. So Shoda, no problem. Yeah.
Good job.
Cheers. Yeah.
See.
And suppose assumption A, I'll show you the assumption in a minute, next slide. Then almost surely we're gonna get third place with that thing on the previous slide. Here's the assumption. I'll kind of, obviously, very abstract. We meant to do it that way. The abstractness gives you a lot of generality. I'll basically go through and just tell you what it roughly means, but we don't have to spend time on the kind of the actual mathematics of it. A is only y is observed, like I only get to see the returns, that's obvious. This Beho's comment was in part B, the number of Q factors is known, and it has to be smaller than the number of observation dates. So you want the number of observation dates to be larger than Q, otherwise we get like divisions by 0, etc. I don't know what happens when Q is misspecified. Super interested, that really cool extension of this, and I think it wouldn't be terribly difficult. The next part is saying that the factor risk is there, and there aren't like the factors are not linearly kind of, you don't have redundant risk factors. That's what it means for that matrix to be invertible. That's assumption C. Assumption D is roughly saying that the data is kind of like stationary, meaning that like the observation that you had on day 1 and day n, those were like, they had the same variance in the specific return part. That's what that means. This one is it's quite difficult to generalize. I'm working on it a little bit, that there are some pathways forward, but this is a difficult one to actually relax. So, and this is where the advantage of taking small n is important. You don't want to take n large, because then at that point you have your first day and your last day are going to be significantly different. In here, if you have 8 risk factors, you can take just 8 days and the theory still works. Sorry, 9 days. Next assumption is, this is saying that the systematic risk B doesn't concentrate onto the noise. So like the residual or the specific return and the systematic component are kind of uncorrelated asymptotically. There isn't a strong correlation there, which is part of the kind of the foundations of asset pricing and return modeling and so on. And then the last part is very important. Let me see what it means. The vector E, the vector of all ones, is not in the column span of B. So like the vector E is not one of your risk factors. This part, you just have to do it separately. It basically is a singularity point, and you have to address this case separately. So it's not like we can't do it, but it's extra work and it's like one thing, and we just don't worry about it, and we move on. So we basically just say you cannot put the vector of all ones as one of the columns of B.
Measure 0 event.
Sure, measure 0 and then, unless you're in a bar ball. Right.
Yeah, bar.
Yeah, bar. Measure 0. Okay. The GPS program. So the rest of the talk is going to be like this. I'm going to try my best to describe how we got the result. I think that there were so many points that this could have completely, like we really should have given up on many occasions here. What I'm going to do is describe to you how you get the result when you have just one risk factor, because there you have a very rich geometry and a lot of intuition to rely on. And then as I go through this part, try to think about how would you solve this? How would you adapt this approach to more risk factors? So right now, what we're going to do is the project that was started here when I was a postdoc with Alex and Lisa, kind of spearheading this effort. And here's the notation. It kind of goes from taking a matrix B and turning it into a vector. That's all we're doing. This was the thing that we started working with, a one-factor model. B is beta. Oh no, a typo. H is supposed to be eta. The little b is the normalized, that's the population eigenvector. So B, little b, is a vector, it's a unit length vector, and that's going to be the population eigenvector. And the little h is going to be the sample eigenvector. And apologies for the typo, the second beta should be an eta. And the z and the e, those are still all the same. Z is, the same thing as e, but normalized to have unit length. And the optimization bias, which is something we came across right away when doing that work, looks like this. And I tried to write it earlier in the multi-Q factor setting in a similar fashion. What you do once you get to this point is you recognize that there are a bunch of things in this optimization bias that you don't know. And the things that you don't know are HB, the dot product between the population eigenvector and the sample eigenvector, and BZ, the projection of B onto the vector of all ones. And it turns out, and this is what we did in theorem 3.1 of that paper, which is we estimated those things in terms of empirically determined quantities, and those were the sample eigenvalues. So this is the theorem there. There's a little psi. It looks very much like the big psi that I used earlier. It's kind of analogous to that. It's a function of eigenvalues, and let's not worry what it is. You just take eigenvalues and you make them into that. Just use that formula. And let's focus on the theorem, which is saying that the dot product between H and B is a number psi. I forgot to mention here, psi is going to be eventually between 0 and 1, which is going to say that those two vectors are not the same in the limit. And the second identity is a little bit more mysterious or curious, but you can see how using these two relations, we have estimates of all the unknowns. So these two relations are giving us the two unknown quantities from the previous slide, and they're going to be determined in terms of sample eigenvalues. That's what these two relations hand over to us. And here's a much better kind of visual representation of what's going on. The psi quantity that you saw is determining the radius of the cone in this picture. It's saying that the sample eigenvector H is somewhere on a cone of radius that is a function of psi around the population vector B. That's this part of the result, the first part of the result, the H dot B is equal to psi. That's the visual representation of that. We know how far H is away from B. The next part is to look at the second part of that theorem, which has the following visual representation. It's saying that the dot product of H onto Z is smaller than the dot product of B onto Z. And visually, that's what this looks like. Now, I guess in other words, I could say H is further away from Z than B is away from Z. And that's consistently true and completely almost surely true, or with probability 1, when P is equal to infinity. On the infinite dimensional sphere, that's what the geometry will look like. And so with this reference frame in mind, by reference frame, I mean with this vector Z in place, this is almost suggesting to us an estimator. We want to get closer to B, and we know that we're kind of lagging behind with respect to the vector Z. And so we're going to move up on this arc. We're going to move up from H towards Z and try to get closer. So a natural estimator in this context is this one, HT. So you're taking a linear combination between H and Z, and you're moving on this arc. So HT is a parametric estimator moving on the curve between the sample eigenvector and the Z. And by the way, the Z comes from the constraint of the minimum variance. That's important to recognize. That's where that vector came from originally. And that's what we're using to guide the construction of the estimator. So you see the estimator moving around, and the question is, can you get the best one, the optimal T, the T that minimizes the distance? And it turns out you can. Everything is done through fairly simple calculations. You look at the optimization bias of HT, you do a lot of tedious calculations, it leads you to a really nice formula. You can see the right-hand side of HT there. It's the optimization bias of H, subtract another term that depends on T. And from there, what do you want to do? You want to find the root of this equation. So you set it to 0. That's all we're trying to do. Set it to 0, you get T star. What's the problem with T star? It has a bunch of unknown things. But theorem 3.1 told us how to approximate them. So we have a plug-in estimator, tau, not T star. So tau star is the thing that we don't know. Tau is the thing that we use to estimate it. And those two are equivalent asymptotically. The ratio as P goes to infinity is the same, equal to 1. And this is what the final result looked like. So this is the work done with Lisa and Alex, started here and completed sort of over years.
Many years.
For many years, too many years, but good years. And we're all happy with the result. And now I guess this is like when Hubeb and I started, battery is running low.
Is there a way to plug in? Yes, thank you.
How am I doing your time?
Well, we get kicked out in about 18 minutes.
I can make it. I mean, the rest is all bonus from here.
I have a lot of questions.
The reason well, the slide is no longer visible, but I just wrote down the optimization bias when Q is greater than 1. And like, you have to start thinking, in this, like, you can kind of put yourself in the situation that Hobaib and I were in, where we're trying to like visualize the problem with Q even like equals to 2.
Really hard.
And so
2 is a lot.
yeah,
bigger
how do
than
you
one.
picture a bunch of vectors all on a sphere, and you're trying to like move them around, and you're trying to find a root of some function? So yeah, we were completely stuck on this. I'll show you a way to get out of it, which is not the way we did it originally. It's a nice kind of trick, but not easy. The point is to say that this GPS program, as I've called it, and the GPS program is basically understand what's happening geometrically, estimate the unknowns, have a plug-in estimator, and get everything to work. That worked well when Q equals 1. And I'm gonna commit, and I think I've already done a good job of convincing you that this is going to be much more difficult when Q is equal to 2, because we lose the geometrical intuition. The thing is, you don't just lose the geometry or your ability to visualize things. You also, oh, wait, there's more, hold on.
Wait, so
The
can't you just, isn't it the whole thing is the same geometry, but it's like a space of spaces, like or something like?
Yeah, so yeah, and I have a picture, so
Yeah,
yeah.
your little
yeah,
vectors are no longer just your regular little vectors, it's like a subspace.
Yeah, exactly. Yeah, and I have a picture like that at the end, so you can visualize it, but we couldn't in the beginning, or we did it incorrectly. And so, yeah, in the end, you can always make a picture once you know the solution. But so at least, we made the picture after the solution. But anyway, I'll talk a little bit about how we got to where we got to. I want to mention, like, do all factors matter? I want to do a quick numerical simulation. Back in that simulation framework we're in, I'm going to pretend that there's only one factor, even though there were 8. Because it's very possible that maybe the other directions, the 2 through 8, don't matter. So I'm going to run the original estimator by Lisa and Alex on this model and see what happens. It does better than PCA, but you can clearly see that the remaining factors matter. And I'll tell you a little bit more about the simulation. If you remove the industry factors, this estimator is great. And there are very good, sound theoretical reasons for why it's great. Style factors, entries of which average out to 0, don't do any harm. It's the industry factors that are doing all of this, wreaking all this havoc to create, a ratio of 8 or 8
We
squared.
haven't quite set them up right yet.
So this is the
Yeah, it's
example,
not gonna
It's not
matter.
gonna
It's not gonna matter, yeah.
this is the example Beho is asking about, which is you messed up the number of factors.
No,
Yeah, oh, that's true. This is but this is like messed up by like a lot. Like I'm thinking like, you're off by 1 or 2. Yeah, this is like messed up by a lot.
So the other thing was that we said that if you're leading, so when we did it with one factor, if your leading factor was far away from the one vector, you didn't gain anything.
Yeah, orthogonal, yeah.
Orthogonal.
That's true for the style factor.
Yeah,
That's
so
one.
the style factors are constructed, you said they're like average,
Yeah.
like 0.
Yeah.
So then,
correcting them doesn't get.
I did want to say all that, yeah.
But correcting, this is the particular correction, which is removing excess dispersion. It turns out there's excess dispersion relative to any base point. And then there are other corrections you could do that'll correct those factors really well.
right.
So
But
this is like
he's correcting purely on the.
he's correcting just one kind of excess dispersion.
I'll show you a general subspace correction at the end if you can stick around that.
So, but that's why
It's at 6 p.m.
6 p.m. Okay,
Your-
6 p.m. is the
your industry one.
that you're right.
Because they're like all positive.
Yes,
They're either
exactly.
0 or 1,
Exactly.
right?
Yes, you got it. Yeah.
Right.
Yeah. But you should know this. Yeah, you did very good. Okay, very good. Very well observed. It's the reason this works is because the industry factors have a projection out to Z. Those are the ones that are wreaking the havoc. Those are the ones that needs to be fixed. Those are the ones that we fix for the rank 1 update.
Makes total sense.
More angles, more problems. It's not just the geometry. This is the most, so like, when I say we almost gave up, or I don't know if we almost gave up, but we probably should have. There are more issues here than just like visualizing and drawing pictures. Maybe we could have gone through that. Here's a nice impossibility theorem. Hobaib hasn't sent me the proof of this yet, but he swears by it. I understand the logic behind it, and we've gone through many examples. In fact, back in the spring of 2001, I was basically trying to go against this result and trying to estimate all of the angles, huh?
Spring of when?
Spring of 2001, I think, 2021. sorry.
2021.
21, yeah,
Yeah.
2001. Well, no.
That's what.
2021, sorry, yeah. Not that. But that's when we started the project. And at that point, like, so let me just get a sense about what we're looking at. In the middle, you see here B transpose H. What is it? These are all of the projections between the population and principal components, all of those pairs. And back in that spring, I thought I could estimate all of them, and I knew that we would need to, or I thought that we would need to, because I was following the GPS program. I was basically saying, we're gonna get to a place where we're gonna need to estimate those dot products. We're gonna need to have every single column in H dotted with every single column in B. I'm gonna have to estimate that with eigenvalues. And then at some point, and I remember the day, it was March 31st, the reason why I remember that, when basically Hubei gave me a counterexample and I stopped working on it. So that's gonna be an issue. But this is where big fail in the GPS program is gonna happen. By the way, this doesn't mean that we don't have limit theorems. Like there's a large PCA literature studying these projections or angles. The issue here is the estimation of those limits. Can you get estimates of them in terms of known quantities? So it's not like, can you get limits? Yeah, you can get limits. The question is, do you know what they are? So the phrasing of the theorem is, there does not exist a function f of the data, right? Those limits are not knowable from sample quantities. That's the key part. It's not that whether the limit exists or it can be derived, it can easily be derived, and it has been. And the takeaway here is that there's no way to estimate the optimization bias. I'm never going to be able to tell you what the optimization bias looks like for PCA. I will have a theorem that will tell you what the length of it is, which is all I need, but I won't be able to tell you what the individual components look like, meaning I won't be able to estimate the individual components. So that is sort of like the first roadblock. Second roadblock had to do with it's not clear how to find the roots of this. Like you're trying to draw things on the sphere, you're trying to find zeros of a complicated vector function, and it's complicated. When you try to plug in, when you try to transform H in some way, that formula can break down. You can see I wrote two equalities there on purpose. When you go from the second one to the last one, you need to make sure that the script H is orthonormal. So if you're trying to like make your estimate different and you're transforming it, if you're not keeping those columns orthogonal, that equality no longer works. So there are a lot of issues, and I feel like I'm running out of time because I hear noise from the top. So I don't know if I should speed up or not. I could, let me see what I could do. I could just kind of
Say the most important.
say the most important thing, but there's so many. I think I've already have said it. What I'll do is I'll show you a very quick trick for how to get the root of the function, and then I'll skip to a couple of quick theorems, and then we'll be out of here. Let's do that. So navigating problem 2, this is the one where we don't have geometrical intuition. This is not actually how we solved it, but I'll give you a sense of how we construct the estimator and how we find the root of the optimization bias. First thing you do is you make the matrix HZ. What we're planning to do is, again, combine in some kind of a linear way Z and the original principal components. The reason for this twist here is that we're going to make them orthogonal. So the reason for the complexity of the second component there is because you want the columns of that matrix to be orthogonal. That's why that second part of that formula is a little bit complicated. But all we're doing is we're making a new matrix, which is adding Z into the span of H. That's the first part. Second part is a linear transformation. We're going to make a matrix. So we no longer have a one parameter thing like a GPS. We have a tau or a T. We have a Q by Q plus 1 matrix T. That's going to be the transformation, and it has to be invertible in the way that's written. And that's the new parametric family that we came up with in the end by slightly different means. Once you plug things into the optimization bias formula, you'll notice that it becomes that thing. And then there's a very quick observation that you can make. So I want you to focus on this, the second term of the optimization bias numerator, the TT dagger. If you look at that and you look at the observation that's made there, and this is just done by direct calculation, then you could just make a direct guess as to what T star the best thing is going to be. And it's going to be the transpose of the thing multiplying the T, and you can plug it in, and on the next slide, I know I'm rushing, but you can very quickly verify that that is the root. That is one very quick way without any geometry to get that. with kind of using a guess. It's not the way we did it, but it's the way we write it now in the paper, for various reasons. That last part is 0. I'll explain this very last part. Why is the last step 0? You're doing a projection of Z onto a matrix whose column span already has Z in it. And therefore, that last H, Z, H, Z, Z, that is just Z making the right-hand side 0. And so now we have our T star. And this brings us back to problem 1. T star is a bunch of angles, and we can't estimate them. So navigating problem 1 is this key lemma that I brought up at the very, very beginning. It has to do with the fact that optimization bias is invariable to the change of basis, as Nick said, and we just have to take a clever change of basis to get out of this issue. We get out of this issue by taking the choice of K that's there, and I'll show you the main theorem that's doing all the work. This is what you can do. You can't estimate angles, but you can estimate kind of the angles squared. There's a different way to say it. It's angles in projected space. And that's a curious finding. I cannot estimate H transpose B, but I can estimate H transpose B, B transpose H. We don't really understand fully why that is. We kind of got lucky just to find it. And we also at the same time noticed that invariant under K. And all of this is kind of several key ingredients that make everything work. You can compare it to the result from our paper with Lisa and Alex. It's very different in the sense that there you can estimate the angle. And again, back when Q is greater than 2, you cannot estimate all of those projections individually. You have to square everything into one thing. I don't fully understand why, but I'm still thinking about it.
But if that's true, if you can estimate angles in projective space, then you can estimate the true angles within a finite subset.
Yes. That's where we've gotten at the end. Yeah.
But
I did hear Nick actually, but
then we're gonna like lose the 3 audience members we have.
exactly.
Start writing in 3 projected space.
Sure. Yes, exactly. True.
Everyone will hate us.
What I was saying is, if you can estimate in projective space, then you can estimate in normal space up to a 2 or a discrete number of alternatives. You've gotten rid of the continuous question because every point in projective space has exactly
Nick,
2
I feel a
points.
pressure from there's you don't realize there's people like at the doors that are barging in, and I gotta find a way to wrap up. I really do want to talk about this, but let's maybe
Nick,
take it
you
offline.
should come down.
Yeah, you should come down. Yeah.
Yeah.
But I'm gonna just roll through the slides. This is a recap. I don't have that much time, but basically we found the T star somewhat magically. We got lucky. We found the K somewhat magically. We found this projective kind of angles theorem somewhat magically. And at the end, we get to that formula for H sharp. That's the summary slide. This is the formula. And by the way, this is the theorem for the optimization bias. You can't estimate the components, but you can estimate its length. So even as you're running PCA, we have an estimator exactly for what the optimization bias is going to be. And Alex, if you want to see a picture, this is the picture that you can write if you leave the sphere. And this always has a connection to James Stein. This is what I call the formula for James Stein for PCA. It's a shrinkage PCA, which is equivalent to what I just presented. A lot to say, but it answers your question about shrinking towards not just the vector Z, but to an arbitrary subspace. Here I'm shrinking principal components H via shrinkage matrix C to an arbitrary matrix M, essentially an arbitrary subspace. So please invite me back. I'd love to talk about this. This could be a whole other hour or two. So thank you.